Okay, so let me discuss now the pulley problem, which is part of your homework assignment for problem set number 4. It is a pulley problem, and I want to show you systematically how you take the constraint of the fixed string into account to determine a constraint between the accelerations of two objects. Okay, so let me make first a very clear sketch of this problem and spend a little bit of time on that. So let's say this here is the ground here, and let's imagine I have here, let me use a different color here. Imagine I have here now an object here like this here. Let me just make this a little bit larger. 1, 2, 3, 4. So let's do this like this here. And as usual, we are not taking the dimensions of this of this object overall into account. So let's see. Let me imagine there's a string here now, and there is a pulley here, and we actually use now a different color for this string here. So here's one string, here's the other string, here's the next pulley, like this here. Let me in fact change this line here a little bit here. Wrapped around here like this, and wrapped around here like this here. I think this is clear. I will make this a little bit more obvious in a second. And then attached here like this here. So let me make this a little bit larger here. Simply thicker here, that line here. So around here like this. From here to here. From here to here. Wrapped around here. And then back to here. Okay? So this would be the actual pulley. Here's this at the center of that pulley. So let me call this pulley B here. This is pulley A. Now what else? What else is missing? So now from here, it is attached to another block. Which I will draw in a second. And here's just a fixed anchor point here. Let me just draw it like this here. This would be a fixed anchor point here. So this little black object here is not moving. So let me just draw here the object of mass m1. Okay. So now this here is object mass m2, this is mass m1, and now there's a force here acting on that object, a known force moving that whole system to the right here. So I think, let's see, I think I have drawn everything at this point. So now the force F, which is attached only to mass m1 here, the mass m2 by itself is attached to of a fixed length to pulley A. Around pulley A is now a rope attached on the top to mass m2, wrapped around pulley A, going around pulley B, and then attached to this black fixed anchor point here. So the blue line here, this is the fixed length of that string. and from block B, from pulley B to to mass M2, that length is also fixed. So this is just the overall sketch of the problem here. Just make very clear what the ground here really is. So now let me draw into the sketch here now various distance lines here, and let's imagine here I have here my coordinate origin here, and I draw now various distances. So number one, the actual time-dependent coordinate of mass M2. So here in the horizontal direction, I call this x2 of t. So when the force F is applied to mass M1, moving the mass M1 from left to right, which is attached to this pulley A, it then drives and moves the mass M2 also to the left. And that time-dependent change of the location is denoted here by x to t from that coordinate origin. Now the same thing now for mass M1 here. I draw also here a straight line and then denote relative to the center that location as x1 of t. So now, besides that, there are various fixed locations now relative to the same coordinate systems. Now, number one, there is the location actually of the of this fixed anchor point relative to the coordinate system, and I denote this distance as d here. That's d. What else? Then the distance of the center of mass M2 and the location of the of pulley B, I denote this distance as S2, and I denote the distance from the center of the pulley center of the pulley A to the center of mass M1. I denote this distance as S1. Okay? So now let me be very clear here. L denotes the distance, the fixed length, so fixed length of the string here. Okay, so therefore, what does that mean? If something has a fixed length, is an invariant quantity, what that means is that the derivative in time of that quantity is zero. That means really in a more abstract way an invariant in a problem. L, that rope, that string wrapped around that pulley system attached to mass M2 on the top and on the bottom attached to that fixed anchor point, that's an invariant in the system. So now let's try to solve this problem. And then what we're really after in solving for this problem is to find an expression for the acceleration A. So the goal here is determine A1, the acceleration of object 1, and A2, the acceleration of object 2, as a function of the magnitude of force F, M1, and M2. Okay, so now we will first draw a free body diagram, and let's first do this for mass M1 and then mass M2. So free body diagram. So now let's see. So let's symbolize mass M1 here, concentrate in a point rather than this big box here. And let's draw here a free body diagram. So what forces are acting on mass M1? Well, it's the force F from left to right. That's number one. Direction matters, magnitude, the length of your vector does not matter. And there's a tension now in the string, that string attached to mass M1, and which is of fixed length to Pulley A, and I denote the tension in this string for the moment as TA. So that's a complete free body diagram. So let's now do the same thing now for mass M2 here. So for mass M2 here, we have now also two forces. One of them is on the top here, the tension in the string here, wrapped around that Pulley A here. We are ignoring completely the masses of Pulley A and Pulley B here. So that tension in the string on the top attached to mass M2 wraps continuously around and then continues towards Pulley B. So there are therefore now, if that mass M1 is now moving to the right subject to the overall external force F here, is therefore object M2 is moving from left to right, and there are two forces now acting on that. On the top, and I denote the tension in that string here as T. And then there is the bottom of mass M2 is attached to Pulley B, and I denote this tension in that string here. Oopsie, drawing here a straight line here. I denote this tension here as TB. Okay, let me just move this a little bit closer here. So here is a complete free body diagram now for both masses. Let me choose now a coordinate system. Let me choose the positive x-axis to the right here. Two independent coordinate system denoting this as I unit vector I and unit vector I here. Remember the discussion in class, I just want to emphasize those are two independent coordinate system, but I do not have to always write here with index 1 and index 2, but keep in mind you choose them really truly independently. So now let's formulate second Newton law here right away. So F net forces on object 1 equals to M1 times the respective acceleration A1, and then F net, the net forces on object 2 times the acceleration A2. Okay, so now let's work this out. So we only have to deal with one dimension in the x direction, so this is really a little bit easier here. Okay, so let's see what we're finding here. So in the unit vector I direction, that coordinate direction relative to drawn here for mass M1, what would we have then? Force F is in a positive direction, TA, the tension, is in the negative direction. So we would have therefore F minus TA equals to M1 times. Now what is the acceleration A1? The acceleration A1 is nothing else than the second derivative in time of that coordinate x1. I mean, you know this. So this is d squared x1 dt squared. I have drawn here plus m1 times the acceleration. A1 by itself is a vectorial quantity. The coefficient is positive because the motion overall is in the positive I direction. So now let's go to the same thing now for object 2 here. And here we have both forces in the positive direction. So we have therefore T plus TB equals to, again, positive M2 second derivative of x2 dt squared. Okay, so let's call this equation 1 here, and let's call this here equation 2 here. So now let's pause here for a moment. There are a couple of unknown things here. We only know force F, we don't know TA, TB, and the tension T in the string. So we have to find some additional constraint and how they're potentially connected here. So TA here, T, and TB here. Let me remind you that TA is the force acting on the right-hand side, that single string on pulley A. TB is the force, the single force acting on the bottom of mass M2 connected to pulley B. And then there's the tension T wrapped around A, and which continuously also goes around pulley B. So what I want to do now is draw a free body diagram for both pulleys, but keeping in mind that the masses of both of them are actually ignored. So the mass of pulley A and the mass of pulley B. And the reason why I'm doing this is purely to find a constraint among those tensions in the string here. All right, so let's first work out the tension in pulley A. So there's a tension, so this is now in the true spirit a third Newton law. There are two objects now in contact with each other, pulley A and mass M1. Mass M1 experiences a force tension in the string TA to the left, whereas the pulley, if you put your mind into pulley A, experiences of tension string TA, but from left to right. So here are two pairs acting on different objects, same magnitude, but in the opposite direction. So therefore we have now the tension in the string TA acting from left to right on pulley A. So I denote this as TA here. And then this blue string is wrapped around here, wrapped around pulley A. So we have now two tensions in the string here. T, you're ignoring the masses of the pulley, and there's another one wrapped around here, T here. So now let's go to object B here, pulley B. And the same thing, mass M2 is in contact with pulley B. Tensions force TB is acting on mass M2 from left to right. So therefore, the interaction pair, the tension in the string TB, is now also acting on pulley B, but in the opposite direction. So therefore, we have here now tension in the string TB, and the masses of pulley A and B are ignored. The tension on the top of pulley A, between pulley A and pulley B, and then on the bottom of pulley B, all those tensions are identical. So therefore you have then here as well tension T and tension T here. Let me draw it like this here. So now we can also formally set up here second Newton law. So let's do this. F net A equals to ma times the acceleration A, and F net B equals to mb times the respective acceleration. Let me call this B and capital A here. So now let's work this out. I obviously forgot here still something, namely the coordinate system. Let me use here positive unit vector direction here as usual from left to right. So now, what do I get? So now I'm writing here I. So now let's translate our force diagram into an equation here. So we have TA in the positive direction, and the two tension forces wrapped around pulley A is to the left. So it's minus 2T, and this is over equals to 0. Why? The mass MA is equals to 0. Okay? Same thing now here. We have now 2t minus tb equals to 0. The mass is equals to 0. So therefore we have now an important constraint which we'll be using, that 2t equals to, on the one hand, ta, which you see from the left hand side, but 2t is also equals to tb. So now we know that ta and tb is the same, and both of them are equals to 2t. So this is an important result that we will now continue to use in the solution of this problem. Okay, so let me now go back and continue formulating the force equations now. So now let me copy this equation here. So this is what we just had before. And now I can replace TA, what you see here, with F minus, and TA we now know is 2t. So I write here 2t equals to m1 times d squared x1 dt squared. So this is equation 1 here. Let me just move this up a little bit here. You see this a little bit clearer. Okay, and then the same thing now for, so this is, oopsie, so this is for M1, and therefore for M2 we get something very similar here. So I can copy this equation here, which we just had before, and now insert here, replace here now TB. So we have now here T, just get rid of these lines here. We replace now here TB, and then therefore have T plus TB, but TB is 2T, so therefore we have actually here 3T. 3T equals to M2 and then d squared x2 dt squared. Okay, and I call this here now equation 2 here. All right. So this is an important result now for now. So what was the goal here? The goal here was now to solve solve for the unknown acceleration A1 and A2 as a function of the force and as a function of M1 and M2. But we have here the unknown tension in the string here. And the acceleration A1 and A2 here, as I will show you now explicitly, is not the same. So this is A1, this here is A2. So we have in fact here 3 unknowns, but we have only 2 equations. So we need another constraint here. So the big question in this problem here is now, how is A1 and A2 related? How can we systematically find this out? And here I go back now to the very beginning and emphasize the fact that that string in blue here is of fixed length. And here you have to now really pay close attention to that here now. And what I want to do now is here copy this part here for the sake of finding a constraint and formulating a constraint in terms of various distances here. So now, how can we do that? Well, the location of mass m1, x1, and the location of mass m2, x2 are undoubtedly functions as a function of time here. However, L is of fixed length here, and the name of the game is now to write down L equals to, in terms of quantities in the problem involving x1 and x2, in a way that you then write down dl dt, namely the invariance of the length of the string equals to 0, and then work out a constraint between x1 the second derivative and x2 the second derivative, from the fact that L by itself is of fixed length. So how can we do that? So let's split up this part here into 3 sections, and let me just highlight them with different shades in blue that you really understand that. So one of them shade is here. This is the upper part. The second part is now the third part will be here in dark blue, and then there is another one here right in the middle. Okay, and then there's this part here. Let me use here green here, one here, and one here, which is wrapped around here. So you have one upper, middle, lower, and then you have these green sections here. So let me just write this down like this here. So we have, oops, not that thick here. So we have therefore L upper plus L middle plus L lower plus, let me call this L wrapped around the pulley, so the green sections here. So let me be very clear about this. This is the green section here, and then what did I choose? The middle section was this color here, and the top section was this color here, the upper section, and the lower part was this section here. Okay, so how can we formulate this now? So L equals to, so now this is, you have to look very, very carefully to that. So let's first work out now the upper section here. So now, if I take now and I just, let me just see something here. Yeah. If I now take, I will wipe this off here, but let me use a different color here in red here, just to indicate what I'm doing here. The length x1 here goes really up to this point here, okay? If I now subtract off the length s1 from here, then I come to here. But I want to have this part here, the upper part here. Well, therefore, if I subtract off now x2 still here, this is drawn here, of course, relative to the center of this box, then I really get the upper length here. Please convince yourself of that. So therefore, the upper section will be x1 minus s1 minus x2. Okay, so x1, then you hop back minus s1, you come to pulley A. And pulley A has this fixed length. Pulley A is wrapped around the string to mass m2. So now if you subtract off x2, then you have that upper length. Now the middle, this is a little bit more complicated. Let's first do now the lower section. The lower section in principle is very similar. Namely, what is that? The lower section here. The lower section, well, let's focus our attention here on that little block here. The little block from the coordinate system is a distance d away. We want to find out the length of this dark section here. So if we take distance d and subtract off first s2 and then this distance s here, then we come to this blue distance of the lower section here. Okay, let me wipe this off here. So what would that be now? So the lower section is therefore d minus x2 minus s2. The middle section I come in a second, and let's do the wrapping around. And imagine the pulleys have a radius, let me call it capital R. So they're wrapped around by 180 degrees. So this would be pi r. You have it in both ways. So it's 2 pi r. Okay. So now we're missing still one section here. And let me move this a little bit to the right here, because this will be a bit longer here. Okay, so now what is this now? The middle section. The middle section, you can, well, let's take S1 again here. Let me go back here. Let's take S1, subtract off S1. Then I'm already here. Okay? Then if I take the distance S2 and add to that x2, then I have the full distance from here to here. And therefore, if I take now x1 from here minus s1, then I'm here, and subtract of this distance, then I come to this distance, this light blue distance in between here. So let me wipe this, clean this up here. So now, therefore, what do I have? Now I on accident deleted here my thicker blue line here. Just go back to this here. So therefore, what do I have now? We have then x1 minus s1, okay, and I subtract of that the sum of x2 plus s2. So this is the middle section now. So please go through this and convince yourself geometrically to that. This is purely a geometrical aspect to that now. But that you get this right is absolutely essential. There's a plus sign missing here for the lower section here. So spend really sufficient time to get this correct here. So now the constraint is now that dl dt is invariant. But let's first summarize, simplify these terms here a little bit. There are many x1, x2s appearing in here. So there's an x1 here, I think that's it. There's an S1 here, S1 here, that's it. And then there's an x2 here, x2 here, and x2 here. And there's an S2 here and an S2 here. So let's write this all together. We have therefore 2x1. We have x2 1, 2, 3. So minus 3x2. And then we have S1. We have 1, 2 minus 2s1. We have S2s, we have 1, 2 minus 2s2, and then we have plus 2 pi r plus d. So now the important thing to realize is d, 2 pi r, s2, s1, and l are all constants. But x1 and x2 depend on time. And you already see here 2x1 minus 3x2. That will give rise to a relation among the acceleration which is non-intuitive, which I mentioned to you in class. So let's calculate now d square L dt squared. So then we get here lots of zeros. All of the 1, 2, 3, 4, counting from right to left, underlined in red, all of them are 0. So, but what we have left is then 2 d squared x1 dt squared minus 3 d squared x2 dt squared, or to make this look a little bit simpler, this is a1, this is a2. You get a very clear relation among a1 and a2. So therefore a1 equals to what? a1 equals to 3, oopsie, 3 over 2 a2, or the other way around, a2 equals to 2 over 3 a1. Okay. Okay, so now we have this. So now we can go back to our basic equation of motions, namely for both masses m1 and m2. Let me just copy them here from before. So this is what we have now, and the name of the game here is to solve for a1 and a2 as a function of the masses and the force F only. So how shall we do this then? So F minus 2t equals to m1 times a1, but let's see, we have here t. We can easily solve the second equation for t. So t equals to, so that would be here 1/3 m2 times a2. But now let's replace a2 by 2/3 a1. So we would have here then 2/9 m2 times a1. 2/9 m2 a1. And let's insert this, let's replace now t here. F minus 2, and then we have here 2 over 9 m2 a1 equals to m1 a1. And you can easily see here that we can solve here now this for a1. We just take a1, we bring this term here, the second term here on the left hand side to the right hand side, to take a1 out and divide by the rest. So then therefore we get a1 equals to F divided by m1 plus 4/9 m2, and a2 is, as I said before, a2 is 2/3 a1, so there's not much to do. So it's 2f 3, and then we have here m1 plus 4, oopsie, 4 over 9 m2. 4/9 m2. Okay. All right. So let me just summarize this end result here. Okay. So I hope you thought this was useful. The actual application of second Newton law is not that complicated, but I think the important thing for you to realize is how to use a constraint of a pulley, namely its fixed length, formulating that fixed length in terms of quantities which are fixed in a pulley. Keep in mind that length S1 is a fixed length, length S2 is a fixed length, namely the distance between the pulley and an object, here pulley A and pulley B and object M2. But the actual masses M2 and M1 relative to that coordinate system change their location as a function of time. And using the fact that this string has fixed length and formulating then the overall length of that string in terms of fixed quantities like S1, S2, and D, but also involving, and that is the important thing now, X2 and X1, allows you then to define an important constraint between these accelerations A1 and A2. So I hope you found this useful. Please go through this problem carefully. And I'm expecting that you write this up and understand this as part of your homework. This will be, expect that you are familiar with this as part of your preparation also for the midterm exam. You can easily imagine a pulley system not only in the horizontal direction but in the vertical direction, similar configuration like that. All right, so let's stop here.